meantime, I'm going to allow people to join.
Adrian, can I ask you a question? Do you know how to get this a pointer on the presentation? I've seen people do this on Zoom.
I honestly don't know how to do that. If you move the mouse,
actually,
we should be able to see you.
Sorry, 1 second. I think stuck on where's my slide 1 and why did it go to the other place? Give me 1 second. I don't actually know what's going on. Oh, where is my mouse? Perhaps I shouldn't do this.
Right, that works.
Okay. Yeah, that works now.
I don't see your mouse though. Can you move it? Can you move your cursor on the screen? See if it's there.
I don't see it actually anywhere. So yeah. I have 2 displays and I've just lost it. All right, I'll try to do my best. At worst, I will use my iPad to annotate or something.
All right. Okay, let's start then. Welcome everyone to our Quantum Matters seminar this week. We have a great pleasure to have Anushya Chandran from Boston University joining us. Anushya had a hard time picking a topic for her presentation because she's working on so many interesting things, but finally she decided for quasi-periodically driven systems. So Anushya, please go ahead. And thank you for joining us. By the way, if you want to ask a question, feel free to raise your hand or unmute yourself. Otherwise, you can post your question on the chat window and we'll read it for you. Thank you. Thank you, Anushya.
Okay, yeah, thank you very much, Adrian. That was a very kind introduction. I'm very happy to be here virtually. So today I thought I would present some interesting recent work. And like by recent, I really mean we just posted it this morning. It just appeared in the archive this morning, right? Nothing like a talk to motivate you to finish something. So I'll primarily talk about the archive reference there and some experimental work with Egg Boyers and Alex Sushkov. So I'm Anushya Chandran, I'm at Boston University, and this is work with David Long, who's my student, Philip Crowley, who was my postdoc until recently, he just moved to MIT, Ivar Martin, and the 2 experimentalists. All right, so let's get cracking. I'd say topology has become very dear to the condensed matter physicist's heart. And the reason is because topological properties underlie quantized responses, right? This was kind of the revolution that the integer quantum Hall effects discovery started. And what's very, very cool about these quantized responses is that they're predicted even in dirty solid state systems with 10 to the 23 particles, right? Like, I mean, this is the reason physics is cool, that we're able to make concrete predictions about such complicated large systems by using some simple properties of band structures, for example. So the quantization of these effects is so precise that they're now even used in the definition of the standard international units, right? So that's quite the claim to fame. So here I have 2 of the dirty solid state quantized effects, which are part of the SI units, the 2D integer quantum Hall effect and the AC Josephson effect. In one case, the transverse resistivity is extremely well quantized. In the other case, the AC Josephson effect has a frequency that's very well quantized. So the integer quantum Hall effect was until very recently used as the resistance standard, and the AC Josephson effect was used as a volt standard. Now they used to define the units themselves. Okay, and so that's the great success of topological properties in equilibrium. And now we can turn around and say, what about the same kind of invariance out of equilibrium? For example, if we strongly drive a system so that its steady state is not something we could describe with a Gibbs distribution, do we still have such invariance? And of course, the important question is the physical properties. So are there associated quantized responses? And if there are, what are they? And that's the topic of my presentation. So do listen on to know the answer, or at least a part of the answer. And this is not an idle theoretical pursuit. there are now a number of platforms that are strongly driven quantum coherent systems. I kind of have 4 examples up there, 2 from the quantum optics world, ion traps called atoms, 2 from the solid state world, superconducting qubits and color defects in diamond. So in all these settings, we're talking about around 1 to 1,000 degrees of quantum degrees of freedom. They are usually out of thermal equilibrium. They are under exquisite control. They can be driven, they can be put into lattices, their interactions can be engineered, and there are detailed microscopic measurements that could be done, many times unimaginable in a solid state, large thermodynamic setting. And if we were to discover topological invariance out of equilibrium in such system, the interest, near-term interest, would certainly be that this would contribute to quantum metrology, to small quantum devices that might be very robust, especially in the NISQ era with noisy qubits and gates. If we have well-quantized effects, those might be quite useful in building a broader platform as a quantum computer. So jumping right to it, what do I have to tell you on this topic? A primary result is on the classification of steady states of d-dimensional lattice models driven by capital D incommensurate tones. So I'll use little d and capital D a lot. Going forward, little d is the spatial dimension, capital D is the number of tones driving this system. And whenever you say the word classification, it should be followed by table. So here's my table. What we find is that when the total small d plus capital D dimension is even, there are no non-trivial topological classes, but when it's odd, there is a classification by the integers, Z, that labels it. I say symmetry class A because this is simply the class in which there are no other symmetries of the problem, okay? So what this lets us do is translate what these invariants are to actual quantized non-equilibrium responses at late times. So as a particular example, I'm going to tell you about a 1D wire strongly driven by 2 incommensurate frequencies, omega 2 and omega 3 in the picture. And I'm going to show you that this wire, when it's in this topological phase, can behave like an energy pump. So it transfers energy from, say, drive 2 to drive 3 at a quantized rate. That's its quantized response far out of equilibrium. On the other side, when d plus capital D is even, yes, there's no classification of the late time steady states that are topologically distinct. However, I'm going to show you, present experiments to you that actually find very long-lived pre-thermal quantized responses. These are experiments done on 19 vacancy centers in Diamond, and I'll motivate why you expect to find them and what the particular observable was. Then, of course, I'll conclude. Okay, so, and yes, I'm sure a lot of you know it's kind of very lonely to give these Zoom talks, so please interrupt, ask questions, slow me down, speed me up, whatever. All right, so here's our setup. So in gray is my small d-dimensional lattice model, and it's being driven by all these incommensurate tones. So by incommensurate tones, for our purposes, you really should just think that the frequencies are not related in any rational way, right? So I don't know, omega d plus capital D is pi times omega d plus 1, something like that. And also you notice my funny notation. It will be clear why I'm choosing to label them starting from d plus 1 to d plus capital D, but just keep that in mind. So what do we need to do? Well, at stating the problem is kind of easy. What we want to do is solve the Schrodinger's equation and describe the steady states. In particular, find quantized responses of these steady states if they exist. So there's a nice way to represent the steady states, and that's what I'm going to walk you through now. It's called the frequency lattice. And for simplicity, to build the ingredients of this lattice, let me assume that we have a small d is 0 system, so really a 2-level system, like a qubit. and it's driven by two coherent tones. Now, I'm going to imagine, to set this thing up for a moment, that they're generated by two cavities. There's two actual cavities whose fundamental frequencies are given by omega 1 and omega 2 in their, and I'm going to treat them quantum mechanically, and we'll come back to our problem of interest, which is when these drives are classical. Okay, so that's our setup on the left. And now let's just walk through how we would describe the phase space in the Hamiltonian of such a system. Okay, so the state space is easy, right? So in order to tell you what the state of the entire qubit cavity system is, I should tell you what is the qubit doing, how many photons are in cavity 1, and how many photons are in cavity 2. So that's my 2D lattice up there with 2 levels per lattice site telling you what the state of the spin 2-level system is, the spin half is. And so this is what I'm going to call a frequency lattice with 2 synthetic dimensions. The synthetic dimensions for us will be given by states of the drives. So here are the states of the 2 cavities. And it's a frequency lattice because kind of the lattice spacing on, say, the x-axis here is omega 1. The lattice spacing on the y-axis there is omega 2, right? You're naturally, in going from photon number n1 is, say, 1 to 2, you absorb a unit omega 1 of energy. So this is the frequency lattice. It has 2 synthetic dimensions. So if I want to represent the Hamiltonian of the qubit cavity system on this lattice, I'll have a couple of different kinds of terms. So the first kind of term I'd have is an on-site term. So this is just literally a time-independent part of the qubit Hamiltonian that has nothing to do with the cavity. This would just, so it would be the same Hamiltonian on every lattice site of this 2D lattice that you see up there. Okay. However, my qubit and cavity do interact, and those parts of the Hamiltonian will give me hops on this 2D lattice, right? So for example, in green, I represented a 1-photon absorption process in which the qubit interacts with cavity 2 in some way and emits a photon. So the photon number goes up by 1 in cavity 2. In red, I have shown a 3-photon process. So some interaction between the qubit and the cavity 1 that involved the increase of the photon number of cavity 1 by 3, right? So when we look at this lattice, nearest neighbor hops would be 1-photon processes, next nearest neighbor hops would involve 2 photons, right? Third neighbor, nearest neighbor 3, and so on. So that's literally what the hops, the geometry of the hops is telling you how many photons are involved, and their amplitudes would of course be set by the couplings of those terms. Okay, so we're almost there. The final part of the Hamiltonian is the energies in the cavities themselves, right? And so the energy in the cavities, in say cavity 1, is linearly proportional to the photon number 1. And we're going to account for this through a uniform electric field. Omega vector, in this 2D lattice, it has 2 components, omega 1 and omega 2, the actual frequencies. And as usual, the potential energy will then be n dot omega, right? And that is the usual energy of cavity 1 and cavity 2. Okay, so hopefully that makes sense. So we kind of have on-site terms, hops, and a uniform electric field. And this is simply a representation of the total Hamiltonian of a qubit coupled to 2 cavities. A comment to make is that this electric field omega vector, or its direction, will be along a non-lattice direction. And that's how we're encoding the fact that these 2 tones are incommensurate with one another, right? So you will hopefully see why this incommensurate nature is important in what I'm going to say subsequently. But at this level, it's simply the direction in which the electric field points is what's differentiating between commensurate tones versus incommensurate tones. Okay, so great, we represented our model on this state space, the Hamiltonian on the state space, and we know how to solve these problems, find the eigenstates, and that tells us the steady states of the qubit cavity system, right? Okay, but my original problem of interest was steady states of a qubit driven by 2 classical drives, right? There were no there were no cavities inside in that setup. So what do we do with our solution for this seemingly different problem? And to make the connection, what we do is we take the classical limit on both our drives. So what we're kind of doing is going, if you wish, to the taking the high photon number limit, right? So we're going deep into the bulk of this lattice. We're forgetting that there is a minimal photon number of 0 in each cavity. And as you go deep into the bulk of the lattice, we're also, there's a controlled approximation in which you can also forget the Bose enhancement factors. So really it doesn't kind of the amplitude to absorb a photon and the amplitude to emit a photon become the same, right? And become the same and independent of the photon number itself. So once we take that limit, we can, how do we interpret the eigenstates on this 2D lattice, which we obtained from the qubit cavity problem? So I've written out an eigenstate there. There's a bunch of indices, but hopefully it's not confusing. So we expect to find, remember, we're driving a qubit system classically. So, whatever crazy things we do, we must in the end only find two independent orthogonal steady states in terms of which we could describe the dynamics starting from any state. So that's my, so that's the index sigma there. It's going to just be 1, 2. It's going to just have to take 2 values. And I can write down an eigenstate on this lattice in terms of basically what its amplitude is for every spin value, as well as for every photon number value, right? So that's what the eigenstates are there. I'm sorry, I can't figure out where my cursor is, so I can't point.
So sometimes it helps to get out of full screen mode. It just shows up.
What's that?
If you get out of full screen mode, the cursor will just show up.
And then I can move it into this slide. Is that what you're saying? Okay,
Maybe.
I will try that. I will try that. Okay. Was that Vadim? Hi, Vadim.
I also have a question. Sorry.
Yeah, go ahead.
Can I ask you a question?
So
when you say that let's find eigenstates, whoa, that's beautiful. When you say let's find eigenstates, what do you expect these eigenstates to be somehow really stationary and physical? Because you might think that the system should just keep heating up in some sense or slosh back and forth.
Oh, good question. So if you just give me one moment, I will finish translating this and then address your question as to how I can interpret these pictures and what the eigenstates look like in terms of what the actual dynamics of the qubit will be, right? That's your question? Yeah?
Close enough.
Close enough? Okay, ask again when I'm done with this. So I tried what Vadim recommended and I still lost my cursor. So I'm clearly technologically incompetent. But I'll try to keep going. So, okay, so we just have an eigenstate on this 2D lattice. All I've written out there is that I'm just telling you that if I have, that thing in yellow kind of indicates its support, those little green blobs are supposed to give you some idea of how large the amplitude is on each of those lattice sites. Of course, I should be giving you an amplitude for every spin state there. But I kind of have this much information, and what is the actual steady state of the qubit? It's the thing I've written down there, the psi sigma of t. And what you're doing is you're replacing every n vector. Every time in this enlarged Hilbert space, you're taking that n vector and replacing it by e to the minus I n dot omega t. Okay. So the thing that I have down there, what it's telling you is I'm supposed to look at this kind of picture of the 2D lattice. And what I have is our picture of the Fourier components of the steady state along two directions. Kind of there are two indices for these Fourier components. One is n1, the other is n2. And so, yeah, that's what this picture is giving me. Vadim, partial answer to your question?
I'm not sure.
Yeah, keep
You're
talking.
not sure? Okay.
I have a question. Maybe it's the same one, but the question is, what this, you say this is the eigenenergy of what Hamiltonian, or what you obviously we can take any state at any particular, if I take some particular time in the I can write my any state of the system as a sum over basis states, which would perfectly good basis states would be sigma prime equals plus or minus, and the set of ends of all of these cavities. But then that's not an eigenstate of any, that's just it is a state in the Hilbert space that would.
Oh, yeah, okay. So this is an eigenstate of the qubit cavity Hamiltonian. So that's what it is formally, right? So
what is the qubit? Well, the qubit of the qubit have, okay, qubit,
yeah.
Okay. Mm-hmm.
So I enlarged my problem, right? So and I added these two cavities. So I honestly have them in my state space, and then I have a regular time independent Hamiltonian in that case, and I solve for its eigenstates, and this is what I have up there. Those are my 5 tilde of sigma. Now, yeah, okay, but I think that was Bert. But there is some an important step that I'm making here. When I take this classical limit, what I'll find is that the eigenstates I basically find shifted versions of this eigenstate that I've drawn in yellow. So much so that countably infinite number of eigenstates on this 2D representation map to the same steady state of the qubit. And it has to be that way because I have to interpret kind of an area number of eigenstates in terms of the stationary states of a single qubit driven by 2 classical tones. So I only need 2 states. And that's the so that's what happens. So a large number of these eigenstates, when you take, they're distinct on the frequency lattice, and they're distinct states of the qubit cavity, eigenstates of the qubit cavity Hamiltonian. When you, however, take this classical limit, they all map onto the same steady state for the qubit. That's what's written down there.
So are you saying there's only one steady state, or there's some number?
There's two. So there's sigma runs between plus minus, but the phi tilde in the first line really, well, perhaps it's confusing. I called it sigma there too. I should really have written phi tilde of alpha, and the alpha there has, there's as many states there as there are eigenstate in the whole 2D lattice. So a large number of phi tilde alpha, the large number of combinations of phi tilde alpha, epsilon alpha map to the same psi sigma of t. That's all I want to say.
But a general steady state would be a linear combination of 2 of these, at least 2 of these, right?
Oh, so by a steady state, I mean that when I time evolve, so a general state will be a linear combination of these 2. I call these steady states because these time evolve to themselves. Does that make sense? These are the version of the Fouquet quasi-energy states that you would think about in the one-term driven problem. Perhaps I should write it out that way, but
time evolve to themselves. They're not periodic, right? So they don't repeat.
They don't repeat, but they the part that's there's a phase factor up front, but the part in the sum repeats. What it is just it's what I've written out is just the Fourier spectrum.
The different frequencies are incommensurate, so it never repeats.
Oh, sorry. So it repeats it's a periodic wave function in on the 2 torus here. So there are 2 drive phases, theta 1 and theta 2. Maybe I should just written out that derivation. So this, if I forgot about all these cavities and so on, I simply take the Schrodinger equation and I treat the 2 drive phases as 2 independent periodic directions because a Hamiltonian is periodic in both those phases. And I do a Fourier transform with respect to both those thetas. And then I have this kind of representation of the a quasi-energy state. So you're right. In time, the incommensurate nature of the frequencies means that the wave function is never periodic. But I can if I represent it on this 2 torus, the part in the sum is periodic.
Okay.
Okay.
I guess if I can just add, this is Bert again, so just to clarify what's going on. So if I look at the original Hamiltonian, the quantum Hamiltonian, there's not 2 eigenstates, but there's an infinite number of eigenstates, energy eigenstates, right? I mean, because it has. But now you're saying, well, we're going to group them in some sense in the if we're looking at just eigenstates, if we want to look at states that have very large n occupation numbers, I can kind of take linear combinations of them or group them into 2 classes that correspond to 2 quasi-steady states with a given sigma. And that's what you're trying to represent here. It's just 2 states that are, or 2 sets of states that are distinguished from each other in the semi-classical limit. Of course, these states are actually, they're related to each other by some time translation. There are many states within each class that are related to each other by a time translation somehow. And then there must be other states that are technically steady eigenstates of the Hamiltonian that are not near these quasi-steady states. Is that correct?
Okay, so everything you said is basically right. So all this is saying is that when you take the semi-classical limit, so that you don't have, as you just said, you're kind of saying that the drives are in coherent states with fixed photon number. Then your state space reduces to just being describing that of the qubit, and then many different distinct eigenfunctions of the cavity qubit problem map to the same steady state of the qubit. And then in response, the other thing you said, the equivalence class is the following. So the yellow blob that I have there is a representation. I can do any translation of it on the frequency lattice that looks like an integer number of units of omega, and any integer number of omega 1 plus any other integer omega 2. So I can kind of take it to any, shift it to any other lattice site on the frequency lattice. That will multiply the wave function by phase, which is exactly canceled out by the change in the eigenenergy. So the steady state, so the size sigma of t that I've written out there, that is the same for a large class of these states. Okay, thank you for all the questions. And apologies, there's another derivation which I probably made it very clear to this audience about what I'm doing. But I did the two-level system coupled to 2 tones. But you hopefully see how this would generalize to a small d dimensional system driven by capital D incommensurate tones. I would now, in this frequency lattice, have small d spatial coordinates. And the remaining will be my photon numbers in the various cavities. Once again, I go deep into the bulk of this lattice to take a classical limit. And I'll have eigenfunctions. Now, those eigenfunctions will represent, in addition to, for a single particle problem, in addition to telling you where the amplitudes of the particle, amplitude of the particle to be on different sites, it also tells you what the Fourier components are for each of those amplitudes along these capital D directions, okay? One thing to emphasize is that this electric field, which kept track of the cavity energy, is only in this, a part of this space. So it can only be in that part of the space that is perpendicular to the subspace spanned by the spatial coordinates. Okay, so what we are going to focus on are we're going to focus on fully localized eigenstates of this frequency lattice. And the reason for that is because we expect that only those will be able to give us quantized responses, in the sense that they will be insensitive to small perturbations. So small perturbations in the sense that if the amplitude of the drives were slightly changed. That would change the amplitude of the hops in this frequency lattice. If the on-site time-independent part of the Hamiltonian change, I would say change the on-site term. So any perturbation that maintains the incommensurate nature of the drives, we would expect that if the eigenstates deep in the bulk of the lattice are just localized on a few sites, they would be relatively insensitive to these changes. And so that's what we're going to classify, because those are the only kinds of eigenstates for which we expect quantized responses. So maybe this is in response to Vadim's question. So physically, what is localization in this frequency lattice? It's just a statement that going back to the example of the qubit, it's just a statement that the qubit is always going to show quasi-periodic dynamics, right? So it's kind of like what we've said is that the qubit's wave function as a function of time has a few frequencies. So there's kind of two frequencies, capital omega 1 and capital omega 2. The stationary state for the qubit builds in maybe, I don't know, one harmonic, omega 1 and 2 omega 1, omega 2 and 2 omega 2, and maybe some cross term, omega 1 plus omega 2, right? But there are a few harmonics. Which harmonics are built in is exactly where it has support in the frequency lattice. And at those harmonics, if I tell you what the state of the qubit is, I've specified its wave function, right? So it's relatively easy to take a local operator, O of t, write down its expansion in the stationary state basis and see that if the stationary states are localized, it's just a sum of a few local operators that oscillate in time, in the sense that to any accuracy, you can truncate that sum, and then you could just see that it's just a sum of few terms, right? So that is the bottom line. In the end, we're saying that we have a qubit, we're going to drive it with two tones, and it's simply going to respond quasi-periodically in time. So it does not have a continuous Fourier spectra. There is, in a way, what we've done by asking for localization is that we're saying that the system doesn't actually explore all these it feels, at least at this level, that there's not much difference between driving with one tone, two tones, three tones, etc. You just add a few more harmonics. So you might worry that we've thrown out the baby with the bathwater. I think that's the saying. So I want to convince you that we haven't. And so to that end, let me just say a few words about what this classification of localized phases is, what it is a classification of. Okay, so I kind of introduced this language already. So what we have from the eigenstates of the frequency lattice is we have quasi-energy states. So in this representation that I have here, what you do is you take an eigenstate in the frequency lattice, and you're basically working out its amplitude in the conjugate theta space. So which is to say, every time you see a ket n, you replace it by e to the minus I n dot theta, and that gives you a set of wave functions with where alpha, that index, runs on the number of sites in the Hilbert space of the small d dimensional system. Okay, so you have these guys. You build a micromotion operator. And it's a unitary operator that maps, takes alpha as some arbitrary basis in the d-dimensional system's Hilbert space. So it's just, this is the unitary that maps alpha to the phi alpha. And you see now that a new object has crept in, capital phi vector. So what are these? So what we're imagining is that in addition to so if I look in the spatial dimensions and I had periodic boundary conditions, I can twist the boundary conditions for in each one of those dimensions. And this vector phi vector keeps track of all those twists, right? So now I have a unitary operator, which provides me a smooth map from the torus with total dimension small d plus capital D to the unitary group. I hope that made sense.
What is capital N?
What is capital N? Capital N is the, I think this is just notation that classification theorists use, but it's basically the capital N is the total number of states in the Hilbert space of the small d-dimensional system. So for example, it would be small l to the d, to the power d, where, sorry, capital L to the power d, where capital L is the linear size of the system. Does that make sense? So it's just the total number of single particle states.
That would be a single particle. Are you doing single particle dynamics or are you doing many body dynamics?
I am doing single particle dynamics, and I will.
Your physical system is a hopping particle now. It's no longer a qubit.
So in what I've done here, yes, indeed. If it was a qubit, then this would be fine. But if I have a 1D system or 2D system or so on, I am imagining that these are tight binding lattice models. So I am talking, so the phi alpha there are single particle wave functions.
Yeah, you're not going to a d-dimensional lattice of qubits.
No, I'm not going to a deep dimension. Yes, that's right. So these are not small d numbers of qubits.
Switch to particle models.
Sorry? Yeah, so small d scales is polynomially scaling with the linear size of the system, right? Not exponentially. I'll try to make comments in the end about the many body case, but yeah, currently I'm just doing tight binding models in small d dimensions driven by capital D units. So yeah, non-interacting mapping. Okay, so the invariant for as a formal mathematical result, the invariant for the smooth map that I had up there is known. It's given by this winding number W. So capital C in front there is some known constant. So we're integrating over the small d twisted boundary condition phases, the capital D thetas, which are conjugate to the photon numbers, capital D photon numbers. Epsilon at JK dot dot is a Levi-Civita symbol, and we're taking the trace of this object, V dagger dV. And all the derivatives there are derivatives of this micromotion operator with respect to either the phase twisting the boundary conditions or these phases associated with the drives. So, okay, that's some a formal winding number. You can write it in a coordinate independent way to convince yourself that it's a topological invariant, independent of coordinates. It's not the way I've written it. You can further convince yourself that it is an integer and that the integer is always 0 when the total frequency lattice dimension d plus capital D is even, and can take any value when it is odd. So this is the invariant that gives us this classification of this table. Okay. Just some comments on the classification before we do something with it. And the point is that the classification only depends on the total frequency lattice dimension, d plus capital D. And the way I understand this is just because we have made this assumption that the eigenstates in the frequency lattice are localized in all dimensions, along all dimensions. So as far as any classification exercise is concerned, there's no distinction between a spatial coordinate and a synthetic coordinate. Maybe in response to David's question, this is kind of where we're using the single particle nature of the Hamiltonian in the spatial direction. Because I think this would break if you had a many body problem.
Wait a sec. The eigenstates, are they localized in both spaces, or they're? I thought you were saying they were only localized in capital D dimensions, and they're not localized in the little d dimensions.
No, so localized in, I didn't emphasize that, it's localized in all dimensions. And I kind of need that for this property of
and your Hamiltonian in the little d dimensions, did it have to be random to make that happen, or?
No. In fact, I'm not going to write out the model explicitly, but we did numerics in a model where on a wire, the localization is a consequence of a uniform electric field. So it's stark localization.
Wait a second.
So it doesn't.
Uniform electric field is where?
Along the wire. So it could be
So you have a uniform
random potential.
field in the little d dimensions as well as in the big D dimensions, you have effective fields. Okay.
Yes. So which is just in response to say that it does not matter how you have obtained localization in the little d dimensions. There is no assumption on randomness, quasi-periodic potentials. Anything you want to do is okay.
Okay. So it's all Stark
yeah.
localization in the whole space. Right. Okay.
In the example that I'm going to show you, yeah, Stark localization in the whole space.
Okay.
Okay. So because we have localized eigenstates in all dimensions, spatial as well as these synthetic ones, a classification doesn't know the distinction between them and thus produces an answer that only depends on the total frequency lattice space dimension. Okay, so I'm going to start using this ALTP. It's a mouthful, so let me just explain what all those words mean. Anomalous to mean that the kinds of topological phases we're going to talk about don't have a static analog. Localized because they're localized on this frequency lattice. Topological because they will have a non-zero invariant, this Wang number invariant. And phases because they, as long as you preserve the incommensurate nature of the drives, these should survive any small perturbations. Okay, so ALTP, that's what those 4 letters stand for. And it's worth noting that the Fouquet problem has been well studied before. In our case, it maps to the capital D's one-tone driving is Fouquet. And its classification is a special case of the one that we have, as it should be. Okay, so yeah, so what we're saying is that Fouquet classification was much more general than at least I understood it to be. Okay, so I'm not a classification person by training, right? So the reason to do this is, of course, to say, so what? Like, okay, we have some invariant strongly out of equilibrium. Can we interpret them in terms of what their physical effects are? In particular, can we find what their associated quantized responses are? For this, I'm going to focus on total frequency lattice dimension. D plus capital D is 3. And well, okay, I don't read Tangora, but here's my English translation, right? So, and what I want to present to you is just the idea that the frequency lattice is really a cohesive representation, can be a cohesive representation of a large class of ALTPs if, as David just said, if we use Stark localization to localize the particles in the spatial dimensions, right? So that's what I'm going to do. So we've constructed such a model. I'm happy to write it out for anybody who's interested. I just want to tell you what ingredients it has. So we designed a model that in 3 dimensions, so it's a type binding model in 3D. It's translationally invariant with a uniform electric field omega vector in a non-lattice direction. And we found regimes of this Hamiltonian in which the eigenstates are all localized deep in the bulk of the lattice just by this electric field in the non-lattice direction and have these non-zero topological invariants. So it's a tricky thing to do because, well, basically because if you keep cranking up the electric field and you'll always get localization. That should make sense because a larger electric field, if this was a qubit driven by 3 tones, tells you that what you're doing is you're cranking up the frequencies of all the drives. So, high frequency driving should do, well, at 0th order, nothing to a qubit. Time averaged Hamiltonian is the same as a time independent one. And so that means those should definitely be localized states on this frequency lattice. And that's definitely what you find, but those don't have non-zero Wang numbers. So we kind of need a sweet spot where you are at strong driving, but not very, very strong as compared to the hopping amplitudes on this lattice. But it can be done. And to do it, we had to add next nearest neighbor and further neighbor hops, which means where we've written down a Hamiltonian, which has multi-photon processes built in, the cavity language. But okay, but if you do this though, what it lets you do is directly build models of ALTPs in various small d dimensions. So in particular, you can take that frequency lattice model, interpret all 3 dimensions as being synthetic, and then that provides you a model of a 3-tone driven qubit, if this was a 2-level system on each lattice side. You can interpret one of the dimensions as being spatial, two of the dimensions as being synthetic, and then you obtain a wire driven by 2 incommensurate tones with a uniform electric field along the wire. So this is what David already asked me about. And, so the states are in the spatial directions are localized by Stark localization. Then of course you can take 2 of the dimensions to be spatial, 1 to be synthetic, and that gives you a Floquet model. And it's a different realization from of a anomalous topological phase that's been noticed in the literature before. Okay, so I think that's all the possible values of small d that you can take. So we get these 3 different models, and we now have to ask ourselves the question: how do I know that they are in anomalous localized topological phases in this kind of frequency lattice, which is not the physical space for the system, for the small d dimensional system. So there are 2 quantized observables that we have in small d plus capital D is 3. The first is a chiral circulating current. So the operator that I've written up there, M of t, this is, it's just the orbital magnetization on this frequency lattice in the direction of the electric field, right? So kind of r cross r dot omega hat, where r is the position on the frequency lattice, here depicted by n. And what you can show is that the long time average of that operator in any initial state, because it's true in every eigenstate of the frequency lattice model, is given by that value I have there on the right, in particular that it's set mod omega over 2 pi times the winding number, this topological invariant. One thing to emphasize, by omega vector here, and what I really mean is just the vector of frequencies driving the system, right? So maybe that was clear already, but just to be totally clear, for example, in the 2-tone driven wire, although I derived it from a frequency lattice model in which the electric field is pointing in a non-lattice direction, once I interpret one of the dimensions as spatial, this is simply a 2-tone driven model. So mod omega here is different than the mod omega in the 3-tone driven qubit, right? So this is simply to emphasize that although I write these expressions that look like they're the same for all 3 physically different systems, they're not. You can tell the drives, the magnetization density or the chiral circulating current can tell, differentiates between the spatial and the synthetic dimensions. But what is this M of t?
Anushia, this is Ji Cheng. I just have a quick question. So, yeah, when you interpret omega in different ways by viewing the little d as 0 versus 1, do you modify the vector n accordingly as well?
So what the vector n would be is that, say, was the wire driven by 2 tones. The first component will tell me the position on the wire, and then the remaining 2 components tell me about the Fourier components. Does that?
Okay. Thanks.
Yeah.
So why do you not include the case little d equals 3, big D equals 0?
Little d is 3, big D is 0.
All the same physics should be there, right?
Yeah. So okay. Yeah. Sure. And I can, if what I'm doing is classifying tight binding models in little d is 3 in the presence of uniform electric fields.
Yeah.
Yeah. So yes.
So
the only reason I didn't include it is it's not a driven problem.
In that time-independent Hamiltonian.
Sorry, David. Yeah, it's a time-independent Hamiltonian.
Yeah, and it'll have these ALTPs or whatever.
Yes, it will have these ALTPs. That's right. And all I am doing now, indeed, the picture I drew up there on the cube is for a static tight binding model. with a uniform electric field omega. And this M of t is written in that language. And what all I'm now doing is interpreting what it means for these driven lower dimensional systems. But you're absolutely right. As a static system, it classifies, as an invariant, it classifies those static systems as well as these driven ones. Okay, so what is this M of t? So in the qubit case, it is the 3 dimensions are all synthetic. So we remember from our mapping to this, or expanding of the problem to include cavities, that we interpret those 3 dimensions as being photon numbers of the 3 cavities. So it's some kind of, when it's non-zero, it's encoding some kind of photon circulation in these eigenstates, which you could also say is it's encoding energy current between the drives. It's really, I should really say it's an energy circulation between the drives. What is it for the driven wire? Well, it's the driven wire, it's a bit of a formal object. I mean, in that case, we're interpreting one of the labels in n vector as a spatial label and the remaining 2 as these photons in the 2 cavities. So it's some composite charge energy current, which involves the particles hopping on the wire, transferring energy to the drive, energy being transferred between the drives and back. Okay, I don't want to push the analogy too much. I just drawn cartoons, but this observable is kind of, it looks formal, at least to me, for the wire. But I told you we could design a concrete model so we can check that they do what we predict. And that's what I have on the left. So what this is plotting is, yeah, you can see what it is. It should be 2 pi over omega times the double braces is the time average magnetization evaluated in the infinite temperature state, so in the identity density matrix. And so we have a regime in which it's sharply quantized to be 1, that's topological, and then we have trivial as well. So this, I should say, was for a qubit driven by 3 tones. Okay, but as happens often in this case, a topological invariant in the bulk is accompanied by edge currents when you make a boundary between regions with different topological invariants. So in particular, for the frequency lattice, this static tight banding model in the presence of a uniform electric field, you can show that there are currents running on the along the surfaces of this lattice perpendicular to the direction of the electric field, omega vector, right? So now, how do we get at the edge of an edge of the frequency lattice? Well, that's very natural in our wire driven by 2 tones problem. So we just go to the edge of the wire. So if you go to the edge of the wire, that puts you on a surface. The 2 dimensions that you have left on the surface are just the 2 synthetic dimensions, which we interpret as the photon numbers of the 2 cavities, or you can interpret them that way. The electric field is completely in this plane. And so if you, in the frequency lattice, if you expect a current perpendicular to this electric field, what it maps to is an energy current, which is quantized, in which the photon number of drive 2 is decreasing in time as the photon number of drive 3 increases in time, right? So that it's an energy current going from drive 2 to drive 3. And once again, we can check this. So this is again, what's being plotted on the y-axis is this time average, long time averaged current multiplied by the time of averaging capital T. So if the energy current is a quantized value independent of time, then current times the time should increase linearly with time. So that's where it's being plotted. So basically it's the slope of these curves that you read out as this quantized current. And it's exactly the value that you predict in the model that we have. So this was a model that we derived from this 3D frequency lattice model for the wire. with the electric field localizing the states along the wire.
So in these systems, is the time reversal symmetry, it's not there. It's not spontaneously broken, right? It's
not there. It's not there.
There's no time reversal symmetry because of the phases. So you presumably can suppress these phases by lining things up so there is a time reversal symmetry.
Yes, but it would be from the driven problems perspective, it would look pretty special. To do that. Yes, but you and not just time reversal. So if you like,
so the sign of this current, whether it goes from 2 to 3, hasn't happened spontaneously. It's due to
yes. So in the static tide binding model presence with the uniform electric field, time reversal is just broken. So there are just flux penetrating various.
It just happens, and that sets the winding number. Yeah.
That's right.
Okay. Thanks.
Okay, so a few remarks. So David asked about whether we're solving a single particle problem or many-body one. So far it was a single particle. We're trying to type binding lattices, but I want to speculate on the role of interactions. And so for the 1D wire driven by 2 incommensurate tones, so 1 plus 2, we expect many-body localization. Why do we expect that? Well, the non-interacting problem had these quasi-energy states that were just localized in all dimensions in our frequency lattice in space, as well as it just involved a few harmonics of each of the drives. So it seems to me that this, I don't see immediately why the structure would be destroyed by weak interactions being added to this problem. So if many-body localization, if these things can be many-body localized at all temperatures, then our results predict new quantum orders at putatively infinite temperature, if this is a fully many-body localized system, right? With this ALTP order, basically having, so for those of you who know the jargon of the field, they have localized bits in the bulk from which one can extract this chiral circulation, and one expects to have localized bits at the edge that function as these non-adiabatic energy pumps at strong driving. Right? So this is not, this is not an adiabatic effect. On the other side, I think this is interesting because it can provide direct experimental realizations of phenomena that have been discussed in the Floquet context in high spatial dimension beyond anything anybody could build in a lab. So for example, one system that we've analyzed is a qubit coupled to a cavity driven by, and if the qubit is classically driven by 2 incommensurate tones and is coupled to a cavity. And we've analyzed it from the context of whether this can support 1 plus 2 ALTPs. It's a bit complicated about as to how to interpret this problem. I'm happy to discuss it if anybody's interested. But we see signatures of 1 plus 2 ALTP in that system. Okay, I think that's almost all my time. So, yeah, maybe I will. This is what I've discussed so far. I want to flash the other results just because I think they're also interesting. So the other results, just in the last minute, were on the 2-tone driven qubit. It was historical about why we were studying this problem. I think Bert, who was in the audience, hopefully still is. Well, we were inspired by his work to study this problem. But this classification tells you that the 2-tone driven qubit, so 0D object driven by 2 tones, has no topologically distinct late time responses. So that can seem a bit disappointing. Except what's interesting is exactly when D plus capital D is even is when we expect very long-lived pre-thermal responses, which are expected to be quantized in the adiabatic limit. Okay, so as a quick, well, maybe I'll just leave you with this slide and flash some data, which is that the what we're doing is when we go to the adiabatic limit, we're going to very weak drive frequencies. So that means in our frequency lattice model, we're cranking down the electric field strength. So much so that at some point it becomes reasonable to think of the response of the frequency lattice model as a linear response to an electric field. Then we just ask ourselves, what are the topological properties of the model without any electric field? And in particular, does it have quantized linear response to an electric field? If it does, then we can translate that effect to a response of the driven qubit. So I don't want to keep you. We did this for an NV qubit driven by 2 tones and predicted a new response that is quantized. It's this fidelity oscillations, and from that we can actually measure. We can actually measure the topological invariant again to do with the underlying band structure in the absence of the electric field. That's really how you should think about this. But we can also study the transition. It's got some interesting properties. And then maybe I will just leave you with that. And thank you. Oh, and thank you to everybody I've worked with on this. And in particular, I want to acknowledge Philip Crowley, who was my postdoc and has really led the charge on kind of all my projects in this direction. So I put it back here.
Thank you, Anushya, for sharing your very nice results. We have a couple of minutes for questions. Maybe 2 questions.
Yeah, I'd like to ask one.
Yes, Greg, go ahead.
Hi, Anushya, can you hear me okay?
Yes. Yes, I can. Was that Greg? I don't know who was
Yeah, that was great.
You can hear, okay. I think my internet connection may be bad. And good to see you. Thanks for the talk. I wanted to ask a question. I did miss a few segments, so maybe it was answered already. But near the end, you were talking about like pre-thermal quantized responses. I guess that's what's shown there in the lower left.
Yeah.
But I guess I somehow missed the Hamiltonian. So, I mean, what kind of interactions are in the Hamiltonian, and how do you like set the difference between short and long times? Like, how do you set the time for the pre-thermal?
Oh, yeah. No, that's a great question. And I mean, you didn't miss it. I didn't, and I'll present it because
okay.
I really didn't have time. But yeah, I can clarify that quickly. So, so what is the Hamiltonian? The Hamiltonian that was engineered in this case corresponded to the Hamiltonian for a simple square lattice Chern Slater model. I think it has different names. Half BHZ model. I call it square lattice Chern Slater model, but it's a simple nearest neighbor hopping model of a Chern Slater 2-band model, and that's this. So what is that? That is sorry. Yikes.
So that's a non-interacting model, though. I guess I'm. So how do you?
Yeah, that's a non-interacting model, and what we're kind of translating is the that underlying non-interacting model in the frequency lattice. Its linear response can be quantized because it's Chern insulator, or it has, well, because it has a topological invariant characterizing its band structure. And we can translate that to responses for the driven qubit, which is really, right, which has, it's not this 2D model. We have this mapping between the stationary states of the qubit and eigenstates of this model. Does that make sense? So what in more direct response to your question, how did they actually do this in the experiment? What they did was, working near the adiabatic limit is very hard for many reasons, but in particular that you don't have qubits that live forever. And so what they actually did was engineered counter-diabatic driving, which basically let them drive this qubit, quote unquote, pretty fast. But they engineered a number of terms that canceled all the transitions you would have in between the states of some target instantaneous Hamiltonian, so that you could do this experiment with finite drives. Does that answer your question?
So are you, so over the course of the experiment, you don't have like dissipation or relaxation? Is that why you have this pre-thermal regime?
So no, not quite. You do. I don't know if I have the data here. that shows it. Well, maybe here you can kind of see it.
I mean, I guess I'm trying to.
So okay, let me back up and just say, so what they're actually doing is they're engineering a Hamiltonian B dot sigma, where B is a pseudo-magnetic, in their problem, it's a real magnetic field, which is time dependent. And that magnetic field that's time dependent has two frequencies built into it that are incommensurate, right? And then there's a particular protocol that they're following for this B of t. Okay, and now it's a real experiment. So their qubit is has a T2, has a T1, and so this is I didn't even describe to you what this was, but these are some fidelity oscillations in this experiment, and the ideal theory predicts the oscillations have constant amplitude, and you can kind of see in the experiment that that's not true. The amplitude is decaying in time. That's one effect of the fact that this is a real qubit in diamond. There are other effects that we didn't model. I don't know, does that? So the ideal model is just a B of t dot sigma. We're driving a single qubit by two incommensurate tones. Mm-hmm. And then we're doing a measurement of fidelity measurement. You're kind of like evolving the qubit with slightly different initial conditions and measuring the fidelity as a function of time. And I didn't go through any of the theory that convinced you of this, but what we predicted was that in this topology, when this frequency lattice model is in a topological phase, then you will see this quantized response in the actual qubit. So what is being plotted here is of the real qubit experiment, no frequency lattices, nothing. Fidelity shows some oscillations. This frequency we can predict and relate to this topological invariant.
Okay, great. No, I think that clarifies it. Thank you.
Okay.
I have a question myself. So, if in the beginning, your slide number 1, you started by introducing this lattice with the photon states and your configuration space in terms of photon number, and so I suppose that if you wanted to describe this in terms of light matter interaction term, you have something like sigma x times a plus a dagger in your Hamiltonian.
Yeah.
Now, that means that basically, unless I'm missing some piece of information, you can only engineer sort of square lattices, right? So you cannot jump diagonally on the lattice.
No, I mean, it depends on what crazy things you can engineer. But maybe I'll say it this way. Indeed, direct hops that are diagonal on the lattice would need something like, I don't know, sigma x, a1 dagger, a2 dagger, right? Plus Hermitian conjugate, etc., which may seem crazy to engineer. But the only thing I want to say in response to that is that you can actually use qubits driven by multiple tones to generate effectively nonlinear media. So how do I say that? So this two-tone driven qubit, which I really didn't talk that much about, in that case, the driving is actually, there's a bare field in the qubit. This is far off resonance from the driving frequencies. So you can really think that the qubit is, it's mediating a response between the two drives. Actually, it's the same thing in there, but I'll have the correct slide here. 1 second. That's okay. So so this is just to say the qubit in this particular driven problem, the qubit is mediating a energy current between the drives. So if you did a procedure where you traced out the qubit, because it is far off resonant with the drive frequencies, you would generate a nonlinear medium. You could generate a nonlinear medium between the two drives. So this is just to say that if you wanted to engineer crazier interaction in this frequency lattice, those are the kinds of things you might do.
I see. Yeah, you can have 2 photon absorption, 3 photon absorption, so on. All right. Any other questions? All right. If not,
actually,
there's one by Bert. Yeah, go ahead, please.
To get a little bit more precise on this. And to get a little better sense of whether, what's the regime where we're going to get something topological and when we're not going to get something topological. So, so in this original thing that we did with a single qubit, and eventually we were, of course, working in the adiabatic limit, which is quite different from what you're interested in. So we're looking at something where let's say you have a single qubit with a magnetic field BZ, which is, say, cosine of omega 1t, and let's say BY is cosine of omega 2t, and then you have something complicated involving both frequencies that's more complicated, driving omega, driving the third dimension. So we have these three incommensurate terms in the Hamiltonian, which these are now functions of time. I guess you could if you Fourier transform them, you can write them as coefficients that, let's say, the cosine omega t is a nearest neighbor hop in one frequency, and the other one is in the other, and then you have something which is more complicated, which is some diagonal or some off diagonal, some more complicated hop in several frequencies, that's sort of the way I would I'm not sure if that's the right way to think about it, and of course there's also the strength of the coupling, which would be the strength of the matrix elements, and whether you're in a topological regime or not depends on ratios of these strengths.
Yes.
So I sort of, and then of course in the case of where it's adiabatic, you're just looking at whether basically when you go through these cycles averaging over a long period of time, you're mapping around whether you're ever going through the 0 point really, or can you avoid it, and whether you get therefore winding numbers. But is there something, and so there, certainly the ratios of the two strengths are important. The absolute values don't matter. Is there something that we can understand similarly in this 2+1 case? Sort of.
Yes. So I didn't write down. Maybe I should have, but I didn't write down the model we actually did the numerics on. Partly because it's quite ugly. But let me tell you what ingredients go in it, and that might in exactly as you're laying out for the two-tone different qubit, and that might help clarify in what regime you could hope to see things like this non-adiabatic energy pump.
Right.
So, okay, so the first point to make, and I think it's easiest said on the, let me just go to this cubic frequency lattice, maybe this picture. So the regime in which, I'll start with the very high electric field limit. So in this model, just to orient everybody, the hops, as Bert was saying, the strength of the hops is set by the amplitude of the drives, roughly speaking. So amplitude of the cosine and sine omega 1t, omega 2t would set how strong the hopping amplitudes are in this lattice, and then the actual frequencies themselves set the strength of the electric field. And then there can be a time-independent piece which can set a field on each side. All right, so if you make the electric field the largest scale in this problem, that becomes high-frequency driving. In that case, we have localization on this lattice, but it's a very short localization length. You can make it arbitrarily close to one lattice site. Now, that is not the regime where you would expect to see anything anomalous or topological, because at least in the cartoon of these eigenstates are that they need to have this built-in circulation. So that means they at least need to have some extent on the frequency lattice to have a non-trivial circulation. So then on the other side, if we lower the electric field, make it the weakest scale of the problem, so coming close to the adiabatic limit, then we may lose localization on this frequency lattice, right? Because certainly for my qubit driven by 3 tones example, The only reason there's any localization in this lattice is because of the Stark effect in all 3 dimensions. So if I keep tuning the electric field down, there might be some, I'm not entirely certain what happens in this 3D case, but for high enough number of tones, we anticipate that the eigenstates actually become delocalized. And so that's also bad because we don't think those will show quantized responses. So the sweet spot where we could get this work is the following. The mod omega, so the different frequencies are all comparable to one another in size. The overall scale mod omega is comparable to the amplitudes of the drives, so the nearest neighbor hops in this lattice, so that we could have localization on a few lattice sites. But then we engineered next nearest neighbor hop and further nearest neighbor hops to basically ensure localization. One piece of intuition that I found helpful was that it's as if that, if you thought that there was and this is only rough, that there's a model perpendicular to the electric field, a 2D model perpendicular to the electric field that's approximately translation invariant. What we're doing by engineering these further neighbor hops is we're flattening the bands of that model so that it's easier to localize it with a small electric field. Did that help? So the regime in which we are able to get this for the qubit driven by 3 tones is we need the strength of the electric field, i.e. the drive frequency is comparable to the amplitudes, but we absolutely need these further neighbor hops, which are exponentially decaying, but we had to go up to 5th nearest neighbor. And we kept them, and we needed that because if we didn't do that, we would lose the sweet spot regime where we had localization as well as a non-zero winding number. We frequently just find localized in the high frequency limit, you lower the frequency and it just, at least on timescales we could look at, it looks like it has a continuous spectrum that is delocalized on this lattice before we could find a sweet spot regime with a non-zero winding number. So does that help?
Yes.
Okay.
Any other questions from the audience? All right. Thank you, Anushya, for a very stimulating talk. There were a lot of questions and a very exciting discussion. So we invite you again to join us next week. And thank you for joining us. Have a great day, rest of the week.